Welcome to practice number 139, and today we're talking about winglets. And we're not talking about just winglets, but a winglet that can rotate and adapt to its environment. So winglets in general are these little vertical end plates on wingtips. They have been around for decades and for good reason. They are very good at increasing the aerodynamic efficiency of an aircraft. And since their introduction, there have been more variations than you can poke a stick at. But fundamentally, they have all the same principle applying. And to understand how a winglet works, let's first talk about the general aerodynamics of a wing. So let me get up paint here first actually so I can draw this. It might be a little bit easier for you to see. And if you're just listening to this on Spotify, you can watch the video on Spotify and or YouTube, and it will be easier for you to play along at home. So over a regular wing, we have, let's say, a wing just here, and we produce lift. We have a high pressure on top, high pressure underneath, so P is high here, and on top we have a low pressure. And we call the underside, because it has a high pressure, the pressure side, and on top, because it has a low pressure, the suction side. And because there is a pressure difference between the pressure side and the suction side, a force is generated. And because the upper surface experiences a lower pressure than the bottom surface, this force is now lift. Now we know that if you have two volumes of air, one at high pressure and one at low pressure, and if you allow these two volumes to mix, you'll find that the high pressure will rush around to the low pressure fluid, and that's how it works. High pressure goes to low pressure. And much of aerodynamics is pressure driven. So bringing that understanding back to wings, if we have these two volumes of different pressures, one on top and one on the bottom, and then we allow them to mix, they will. On an airplane wing without a winglet, exactly that happens. So we have the flow going from underneath and it comes onto the top. And this happens at the wing tip. So let's say we have the fuselage, which is here. Then we have the wing coming out. Then we have the end of the wing. And we're producing lift along the entire wing. When we get to the end here, we still have high pressure underneath, low pressure on top. So the fluid really wants to roll around onto the top of the wing. And if you don't stop that from happening, then you will get something called wingtip vortices. And we're all very familiar with these things. Now, I've been fortunate enough to study this exact phenomenon for several years, and there are many different ways of explaining how and why this phenomenon is bad for aerodynamics, and all are valid. It's just that they look at them from different angles, but in the explanation that I'm going to give you, I'm going to go through a very visual way because I think this helps us understand what's happening without having to dive into the heavy maths. So the reason why this phenomenon of having these wingtip vortices forming is bad for aerodynamics is because these vortices, as we produce them, they're effectively wasted energy. We're not using them for anything. We're not using them to produce lift. We're not using them to produce drag. We're not using them to, charge a turbojet or whatever. I don't know, whatever you want to use it for. We're not using it for anything. So because we have these vortices present without them actually producing anything useful for us, they are by definition, wasted energy. And that means that we have more drag. So a winglet is a very clever design in that it is so simple, yet highly effective in reducing and even mitigating a wingtip vortex completely, and thereby reducing the drag of a wing and increasing the efficiency of the airplane. So how it works is that in its most basic form, it is just a flat plate sticking up into the air. So we just have now a flat plate coming here. And this literally just produces a physical barrier between the high pressure air underneath and the low pressure air on top, hence stopping these two volumes from being able to mix and produce this wingtip vortex. And that reduces the drag. Now, that is the basic operation of a winglet, and one major problem with them is that they are typically fixed, which means that they are installed and they don't ever move in relation to the wing that they are attached to. Now, if an airplane solely operated at one flight condition throughout its entire flight path, then this would be fine, because you would just install the winglets to suit their flight operation. But all planes have different flight paths, and while most planes spend most of their time at cruise, other parts of the flight are also important, such as takeoff, and takeoff actually uses quite a bit of fuel, considering how short a time span takeoff actually occurs over. It occurs over a few minutes, yet it uses maybe 3, 4, 5% of the fuel of an aircraft. That's how important the takeoff phase is. So as such, it would be better if you could change the winglet to maximize its effects based on the flight phase the plane is in. And that's exactly what this study is about. So this is going to be split over 2 podcasts. In this first podcast, we've gone through the theory of winglets, and we'll go through the setup of this study and some of the preliminary results. Then in the next podcast, we'll go through the results in more detail. So to look into this idea, which has been researched for some time in terms of being able to change the winglet to adapt to its flight path, to its flight phase, these researchers in this paper is called, we're using this paper by these researchers, called New Aerodynamic Studies of an Adaptive Winglet Application on the Regional Jet CRJ700. So this is an open access paper. You can find a link in the description, and it's there free for you. So the CRJ700 is probably the most popular bombardier plane, or maybe at least the top 2 most popular planes. It is a small passenger airliner, and figure 1 shows the way that the winglet can be moved in this study. So we have the bombardier airplane here, and the winglet is just in these little breakout pictures here. And typically a winglet will be up to some degree, so we're pointing up maybe not 90 degrees exactly, but maybe 70 degrees, 60 degrees, whatever. With this winglet, it can go anywhere from 100 degrees, so well past completely upright, and then swinging all the way down and to minus 100 degrees, it looks like, or anywhere in between. And it rotates around the x-axis, so the direction of flight. So how did they look into this topic of being able to investigate these adaptive winglets on these airplanes? So they used CFD, and in particular RANs. With their mesh, they say something very interesting. They say that for simulations using a different angle of attack from 0, it was preferred to rotate the aircraft instead of the flow. So we see in figure 2 here, we have just these little breakout parts with the CFD block here, and they said that they wanted to rotate the airplane with different angles of attack instead of changing the incoming flow. Now, why would you do that? Why would you prefer to do this instead of changing the inlet flow? So let me draw this again so we can understand what's going on. So with CFD, we always have to make a domain. And in regular CFD, non-aeronautical engineering CFD, we often just make a cube. So we say this is the domain here. And we might have it coming out like this a little bit. And this is the domain. And we have the inlet here, the outlet coming out, and the inlet is a flat face. It's a rectangular prism. An alternative way of doing this is we actually make a very similar domain, but then at the front, we curve it. So this is called a C shape. Now, why would you want to have this C shape instead of this rectangular prism? And I should mention, this is the inlet now. This is the outlet still. And this way here is quite a common way, and I prefer it. So let's go through some of the reasons why this second way would be better for the study than the first way. Because the way that these researchers described it, they're using this method, which is a rectangular prism effectively. And so why is this? Well, when you have a rectangular prism for the domain, you have to rotate the geometry and remesh every time you have a different angle of attack. Because if you were to change the flow angle instead to achieve a non-zero degree angle of attack, so let's say you wanted to have the flow coming in this way, and to say, okay, the angle of attack is now 3 degrees and you have your regular object still flat, the inlet is flat, so if you were to come down to the corners here, the flow's coming in, and you might get flow separation around this region here, and you're trying to force flow through maybe even a plane that it shouldn't be coming through. So this makes the CFD very time consuming because you have to remesh every time you're doing a new angle of attack. A better way of setting up this CFD is by using this C-mesh domain. So the reason why this is important is because you can keep your geometry flat and you just change the inlet flow angle. So you can say now it's coming in at 3 degrees or whatever you want. And this is fine because when you get to the point where you meet the side, you're not going to get separation over this point here, and the boundary probably won't experience this flow income anyway. So you don't really get a problem with the flow coming in. So what this means is that you don't have to remesh the flow every time you want a different angle of attack. You just set the boundary condition to be different, and that takes like 2 seconds, as opposed to remeshing takes like, for this particular case, which we'll get into in a second, that would probably take 3 or 4 hours. So using the C-mesh way is far more efficient than using the rectangular prism way for aerodynamics, and particularly when you want to change the angle of attack. So you save a lot of time and a lot of work. I'm not sure why these researchers didn't do it this way. I've looked at the paper and I can't see any obvious reasons. Perhaps I'm missing something, but perhaps it might be just that they weren't aware of the second approach, the C-mesh domain. I don't really know. Anyway, let's move on to the rest of the CFD setup. So they say that they had a mesh of 11.4 million cells, and this resulted in a Y plus between 100 and 200. So is this Y plus value acceptable for the simulation? I'm not entirely convinced because of a couple of things that they say. First, they say that they use the Spallet-Almaras turbulence model for the initialization process. So what that means is when you have your CFD and you have a lot of cells and you want to run it, if you were just to run it from scratch with your very high accuracy settings, that will take a lot of time to do, because you have a very small time, well in this case not a small time step, but you have the flow starting at 0 in terms of the Mach number, and then you have to march it along to get to the point where it's actually a steady state flow because it's RANs. If you use a much simpler setup, so for example here they're using a Spalart-Almaras turbulence model, this is only a one equation turbulence model, which means it's quicker to solve. That means that you can get to the point where you can get to the steady state and the actual results quicker. So the Spalart-Almaras turbulence model is pretty good. It's actually an aeronautical turbulence model. It was designed for that. But they then say that they chose this model because it was the most stable. What that means is that this CFD was prone to divergence, and that's not good. That's often a function of a poor quality mesh, and in this particular case, it's probably because they had a very high Y plus value between 100 and 200. Alternatively, they could refine the mesh, but that would also increase the amount of time it takes to solve your CFD. They then said that for the actual simulation, once their CFD domain was initialized, they then switched to the SST K-Omega turbulence model because of its accuracy. So the SST K-Omega turbulence model usually needs a Y plus below 5 and ideally below 1. So having a Y plus between 100 and 200 is a little difficult to be okay with. So let's move on to the validation to see if this potential problem came to fruition. So the validation process that they used was quite interesting, and I would say I'm quite impressed with it. So the way that they went about it was that they had 35 flight conditions that a CRJ 700 typically flies at. They had data from reference cases that they are comparing to. Because they are looking at 35 cases, I would say that this validation process is among the most thorough that I have seen in a paper before. It's very, very nice. These 35 flight conditions ranged in Mach numbers, altitudes, and angles of attack. So they went from a Mach number between 0.31 to 0.79, an altitude of 5,000 feet to 30,000 feet, and angles of attack between -2 degrees and 4 degrees. So it was quite a thorough validation process. In figure 4, they then plotted the errors in the lift, drag, and pitching moment coefficients from left to right, with the reference data to see how the validation case lined up. So the bottom axis here is the residual error between the lift coefficient, drag coefficient, and the pitching moment coefficient, and the number of instances is on the y-axis, so in other words, how often it fell into this histogram bin. So overall, it looks okay, not great, but okay. There is obviously some error, so let's talk about these errors that they are finding. In the lift coefficient, it is okay, I think. The error is around about 2% based on the general lift coefficient of a CRJ 700 airplane. But for the drag coefficient, I think the errors are around 5% on average. So in order for the CFD to be valuable, the changes must be greater than 5% for the drag coefficient, and the changes in the flow physics shouldn't mess with the results too much. This last point is important because while the percentage differences between the forces are important, if the underlying reason for these changes is profound in the sense that the flow physics is greatly altered, then extending the CFD to other cases may result in worse errors. Let's discuss this a little bit further. So an example of this change in flow physics might be if the flow changed from laminar to transitional or even turbulent. This change in the flow is very important and it will affect the forces more in certain situations than others. Now fortunately in this particular case, we are dealing with an airplane in cruise. This means that the flow physics is fairly stable. So the reasons for the errors in the forces should not be because of profound changes in the flow physics, but because of just general small errors that perhaps compound over time. So they're not really the flow physics may not be an issue here, which is good. Hence, I don't expect these errors to be too bad. So we can conclude that in this particular case, if the changes in the airplane's performance exceeds 5% with winglets in different configurations, then these changes can be trusted over these errors that we are finding in the drag coefficient. For the lift coefficient, if they're over like 2%, then we can trust that too. So let's move on to the initial results that they found for this study. So the investigation into the adaptive winglet study was performed for several different flight conditions. In table 2, actually in figure 5, we see some meshing of the winglet, but in table 2 we see the test conditions that they looked at. So this is a test space. Just briefly, they investigated how rotating the winglet around the x-axis affected the airplane's performance from altitudes ranging from 5,000 feet to 30,000 feet. From Mach numbers from 0.31 to 0.79, and angles of attack between -2 degrees and 2 degrees. Now with this Mach number, I should mention that with their CFD, they did choose a compressible solver, which is very good. I mean, all the Mach numbers are in the compressible regime. I wouldn't expect that the airplane was reaching its critical Mach number yet. So the critical Mach number is the velocity at which you'll start to get sonic flow over the airplane. So because we have an airplane and we have wings and we have fuselage, etc., when the flow goes over it, it will start to accelerate in certain regions, which means that the velocity in this region will increase. If you have a Mach number of, let's say, 0.98, then there's a really good chance that over the airplane at some point, the flow will either be sonic or even supersonic. And this results in shock waves and also an increase in drag. For a Mach number of 0.79 for an aircraft, that's very unlikely to result in, for an airliner at least, to result in sonic flow happening over the airplane. Typically, you need to get around 0.88, 0.9 for that to happen. So this is below that region, but it's also still within the compressible regime, so that's fine. So figure 7, as we'll scroll down to, shows the effects of changing the winglet angle in the test space. So this is pretty cool. It has a three-dimensional test space with the Mach number on one axis, the winglet deflection angle on the other axis, and the lift or drag coefficient on the third axis. Interestingly, the winglet angle doesn't really change the drag coefficient very much. So we can see in this 7b here, they have different Mach numbers ranging from 0.31 up to 0.79, and the winglet deflection angle from minus 100 degrees to 100 degrees. And the drag coefficient doesn't really change too much along that axis. It's maybe a couple percent. I would say at best, we're looking at maybe even a few percent, which I think is within the error anyway. So we can conclude that the drag coefficient isn't really affected by the by the winglet, and we'll discuss this a little bit more in detail a little bit later. Let's move on to the lift coefficient. So the lift coefficient does change quite significantly when you change the winglet angle. We can see here that there's quite a bit of curve to this surface here. I can see changes of around 4% quite consistently across this space. And with the best lift coefficients being obtained when the winglet angle is 0. So in other words, when the winglet is completely horizontal and not pointing up or down. This 4% is more than the error that we found with the CFD, so I think that this change is valid. So one possible reason why the lift coefficient has increased when the winglet is horizontal is that I'm not sure how these researchers took into account the additional surface area of the winglet. So in other words, if you have the winglet horizontal, it's effectively just more of the wing. And if you were to get your airplane and you have the winglet horizontal, then you calculate you have the lift force, then you calculate the lift coefficient with the old reference area without taking into account the additional area that this winglet has added to the wing, then you're going to get a lift coefficient greater just artificially because the surface area is not accurate. If you take into account that surface area, then you get a more apples to apples comparison. I'm not sure how the researchers did it in this case. They might have used the old reference area to calculate the lift coefficient of the new airplane effectively, but they may not have. Haven't seen that in the paper so far, and we'll go into more depth in the next podcast. That is just one reason. So in the drag coefficient plot, though, let's get back to this. I'm quite surprised that the change in the winglet angle didn't affect the drag coefficient. I mean, when the winglet is completely horizontal, that is effectively like just having a slightly longer wing, which should be conducive to producing the wingtip vortex and hence induce drag. But that is not reflected in this figure, so at least not very strongly. So I think that either there is something else going on here, or the error in the drag coefficient is too great to see these changes. Because sure, having an additional winglet, like extending the wing, increases the aspect ratio of the wing, which reduces the or increases the efficiency of the wing, reduces the induced drag a little bit, but not nearly as much as having the winglet just upright. We should see quite a few percent change in the drag coefficient, which I think is just engulfed from the overall increase in the drag error, sorry. So those are the preliminary results that we found from this study. In the next podcast, we'll go through some details and at different flight paths and different flight phases. But that brings us to the end of this podcast now. So if you liked what we went through, make sure to hit the like button. And if you want to see more like this, click the subscribe button so you can see more. And we also have playlists so you can look at them as well. And if you want to make your experiments 2 to 4 times more accurate, check out Mr. Hawk. Essentially, we make your experiments that much more accurate. In some cases, even 50% more accurate. And if you want to get better at CFD like we've been going through now, and or theory, check out our courses in link description. And I'll see you next podcast. Peace, amigos.